I want to continue with our discussion of Fourier filtering. Now, Fourier filtering is an alternative to convolution masking. We looked at convolution masking. We have an image and a mask, which is either a smoothing mask or a sharpening mask. A smoothing mask like a 1, 1, 1, 1, 1, 1, 1, 1. And a sharpening mask, which is a large number in the middle and smaller negative numbers surrounding it. So we have our mask here, and we convolve the image with that mask, and we get the result, either a smoothed image or a sharpened image, depending on which mask we used. And we're doing the convolution of this with the mask to get that. An alternative to doing that is to take the Fourier transform of the image we start off with and then multiply it by a Fourier filtering. This is a mask, this is a filter, this is a multiply, this is a typo in the book. This should be straight multiply. So we take the Fourier transform and multiply it by a filter and get a result, and then take the inverse Fourier transform, and we'll get to the same place as if we did this convolution, if the filter is the Fourier transform of the mask. And that's why I'm very clear to talk about the convolution masks in the spatial domain. Image J mixes it up a little bit, and filters, Fourier filters in the frequency domain. So this pathway is an alternative to this. Fourier filtering, which is this multiply by a Fourier filter and get back to the spatial domain, is an alternative to straight convolution. And although it looks like a more complicated thing to do, because the Fourier transform and the inverse Fourier transform are very efficient operations, and because multiply is straightforward, this is a multiply, then it generally takes the computer a shorter time to do this than it takes it to do convolution. Convolution is that sum of products and moving the mask through the image pixel at a time, doing a sum of products. So that's a computer-intensive operation that takes a long time. We'll generally try and do things with Fourier filters instead of convolution, where the filter we use is the Fourier transform of the mask. So let's open image J, and I want to show you how to make a filter. We'll go File, New Image, make a 256 by 256 black image, and then have the circle tool here, this ellipse. Holding down the shift key makes it a circle. So we'll make a circle, make a pretty small circle, position it in the center, go to Edit, Fill it with white, and we've got our filter now. This is a pillbox or brick wall filter. We're going to use it in the frequency domain. We're going to multiply a power spectrum by this, which will be a low pass filter. It multiplies this by 255 or by 1, and then multiplies this part of the power spectrum by 0, so it doesn't let these frequencies through. It's a low pass filter, passes only these. If we want a high pass filter, we can take this and use the invert and make it a high pass filter, so it passes all these frequencies and doesn't pass these frequencies. And this is the cutoff frequency, and we change that by making different size circles. So I've already done two previously, this low pass filter and this low pass filter, and the high pass filters just the inverts of those. If we look at this one, actually this low pass filter, and go to Fourier transform, we see that it is in fact a Bessel function. And you can compare that with the image in figure 7.810 of the book, 7.8 part 10. It's a Bessel function, but we won't get into the math. But these are brick wall or pillbox filters. We're going to take an image like Lena, and in order to do this multiplication and have these here as frequency domain filters, we're going to go to process FFT. We're not going to go to filters. Now remember, filters is a misnomer here. It should be masks. And that's when we did all the convolution masks. Instead, we're doing filtering in the frequency domain. And we're going to go down here to custom filter. If we do that, it asks us what filter we want to use in order to filter our image, Lena. And we're going to use this one first, Untitled 1, which is a low pass filter. And if we do that, the result is this here. It's quite a dramatic result. Let me try it with this one again. So we're going to take Lena, and go to process, custom filter, and use Untitled 2. It's a low pass, but it passes these frequencies, doesn't pass those. So we do that. It passes these frequencies in Lena and doesn't pass the high frequencies. So we get a rather blurred version of Lena. A lot of ringing. That's due to the sharpness of the cutoff here. And in general, we wouldn't use a pillbox filter like this here. We'd try and blur this cutoff a bit so as not to get all this ringing. But we get a blurred version of Lena, just like if we were doing convolution in the spatial domain with a filter like, with a mask like 111, 111, 111. So this is equivalent to doing that. If we reduce the cutoff frequency and only let a few frequencies through, then we're only letting a few of the low frequencies through. We're missing a lot of stuff here, which is building up Lena. And of course, we're losing the high. So we've blurred it too much here, but it is a blurring function. If we use Lena, let's make another copy of her. We can filter her with a high pass filter. Let's use this one first. We'll go to process, FFT, custom, and we'll use Untitled 3 and click OK. And we're letting through just the higher frequencies. The higher frequencies are the edges. So we see the edges in Lena. If we better make another duplicate of her. If we let through more frequencies, including some of the middle frequencies, then we'll go process FFT, custom filter. We'll use Untitled here, and OK. And the result is that. High pass. High pass actually sharpens her up a bit. So I'd like you to make some filters here and use this process FFT custom filter on different images to see what you get. If we look back at the book and scroll to page 223, 1921, 23, this is the section on it, 223, the section on frequency filters. We were looking at brick wall filters. Low pass brick wall filters pass all the frequencies up to a certain cutoff and remove all the frequencies beyond that. So it's a 1 up until a certain frequency, and then it multiplies the power spectrum by 0 after that. It's a brick wall or a pillbox. You know, we've seen it like this here, but we could look at it in 3 dimensions. plotting up the 1 or the 255 and the 0 outside of it. So this is a low-pass brick wall filter in the frequency domain to do Fourier filtering, low-pass Fourier filtering, which is the same as convolving the original Lena image with a mask that looks like this, which is the Fourier transform of that. The Fourier transform of this filter is this mask plotted out, where height is the larger numbers, and it's all of these little undulations here that are causing the ringing effect that we were seeing with that. We see it when we use a mask, but we also see it when we use a filter. If we go on a little bit further, let me see, not quite that far. Let's look here. We can change it from this sharp mask, and we can make it less sharp by using a low-pass Butterworth filter, which looks like this here. I'm going to multiply it by this, where n is the order of the Butterworth filter. And we can see that in figure 33. So figure 33 is here, right? Instead of having a sharp pillbox shape, we smooth it out. And we smooth it out by using different values of n. Or we could use a Gaussian filter. This is a Gaussian filter. Here it smooths it out. There'll be no ringing effect. This filter, we're plotting spatial frequencies from 0 up. If we were to plot negative frequencies, then this would look like a Gaussian. And we know that the Fourier transform of a Gaussian is a Gaussian. A narrow Gaussian gives a wide Gaussian. A wide Gaussian in one domain gives a narrow Gaussian in the other. But a Fourier filter is comparable to doing convolution with a mask that looks like this. This is a weighted averaging mask. This is like a 121, 242, 121 type of mask. That would be the profile through the mask. So those are equivalent either in the spatial domain, convolving with a mask like this, a weighted averaging mask, gives you a certain result. The same result can be obtained by going into the frequency domain and using a filter of this shape, another Gaussian. Conversely, we can have a high-pass filter, which is a brick wall like this one. Or we can have Butterworth high-pass filters and change the order of them. But a high-pass filter looks like this. It lets through the high frequencies and doesn't let through the low frequencies. If we take a Fourier transform of that shape, it's not one of the shapes that we usually do, but if we take a Fourier transform of that, we get this, the equivalent mask in the spatial domain. So doing high-pass filtering is like convolving the original image with a mask that has a large positive number surrounded by small negative numbers or 0. So Fourier filtering, an alternative to convolution masking, and usually much faster. I want you to do activity 7.7 and 7.8 from the book. They require a couple of images which are in that chapter 7 images.7z zipped file, which is the beginning of module 4, which you should have downloaded, unzipped, and put in your 345 images folder. So you'll need those couple of images, and the rest of the files that you need you look it up in the book 7.7 and 7.8. The other files you'll need there are in Files in Canvas. So you look through Canvas alphabetically and find those files. And that's all we're going to do on Fourier filtering.